All right, so we're going to look at the law of conservation of mass. So first, you got to understand the book definition of the law of conservation of mass, which simply states that mass cannot be created nor destroyed. So when you're looking at a chemical reaction, whatever is on the reactant side, for example, on this side we have 2Na plus a Cl2, so we have the reactants and we have the arrow, which is the yield, and then we have the final product. When you use your T-chart method that you already have learned, and you count the elements and atoms on the reactant side, there should be the exact amount of elements and atoms on the product side. Reactant side on the left, product side on the right. The yield sign is the arrow. And so that's how you decide if the law of conservation of mass is upheld or not. If you're noticing a discrepancy when you are comparing T-charts from the reactant side to the product side, if there's a discrepancy, then the law of conservation of mass is not upheld. But if there isn't a discrepancy, it is. So we have two potassium atoms in this example down here, and 2 chlorine atoms, and they get rearranged, but there's still the same amount. And it makes a new product because the elements have been rearranged. All right, moving along. Chemical equations are used to describe chemical reactions. We have the PbNO3 plus the Ki on the reactant side, yielding this. And as you will learn soon, you get these two liquids combining, these two clear liquids combining to create a solid, which is also known as a precipitate. And you'll learn that, or a precipitate, whatever you want to call it, but you'll figure that out later. But these substances on the reactant side yield these substances over on this side, which have been produced during the chemical reaction. And this is what it looks like in chemical formula state. Reactants yielding product. Law of conservation of mass upheld if you were to T-chart it and count the elements and atoms. And you'll notice that you could actually count the molar mass, how much it weighs, and notice that it would be the same. The molar mass would not change. Yep, mass never created nor destroyed. So again, molar mass, it's real simple, and you're going to see questions like this coming up. Let's talk about this one right here. You have 3.5 G plus question mark equaling 5.0. Clearly you guys know how to do this math, how to decide what needs to be added to 3.5 to get that 5. Or you could do it like this. The 2.1 plus 8.5 gives you. Just check those out. You should have no problem handling this basic math. It's simply counting and adding. But there's some answers for you. All right, you can go through a couple of these just to make sure you got it right, but I'll pop the answers in. You need to know how to do this. So maybe you didn't do any of those, but you are responsible for knowing how to do that math. Solving for mass, when the concept is shown with a chemical equation, nothing changes about how it should be solved. For example, hydrogen 16 grams plus 128 grams of oxygen gives you how much water as far as the molar mass is concerned? That would be 144. Same thing here, another question. You can look at that, pause it, check it out if you wish. Another one here. How much oxygen reacted with carbon if 88 grams of carbon dioxide is produced? Do that math, figure that question out. Same thing over here. So they're putting coefficients here in the chemical equation. I mean, it really doesn't matter because all you're doing is times, if you take these 4 here and times it by, well, you're going to times the K by 2. Never mind what I just said. What they did was they wanted to know if there was no 2 here, they wanted you to find out how to, you know, if you could recognize how to make it look balanced in a chemical formula state. So you would just put the 2 in front of the K, so that coefficient would go to the K, showing you that there's 2. And you could do the same thing on this side because it says KCl. You put a 2 there, and that shows that it's 2 Ks. And then hippity-hoppity, distribute the property. The 2 goes to the K. The 2 also goes to the Cl. So you multiply 2 by 1K, giving you 2K, and 2 by 1Cl, giving you 2Cl. The coefficients multiply through the entire thing. Once again, hippity-hoppity, distributing the property. So 2 goes to the Fe and the Cl, 4 goes to the F, 3 goes to the Al and the Cl, 6 goes to the K and to the S. And because there's no, remember that if there is no number there, we always assume 1. So 1, that is 1 molecule of CaBr2. So write how many atoms of each element are present after the coefficient is added. So I'll do this first one with you. Once again, we distribute. So 2 times 1C would be 2 here. And then 2 times 2 S's would be 4 S's. So go ahead and work through the rest of those. Make sure you have that handled. And then here's the rest of the answers. You can determine whether or not equations are balanced using the simple accounting method, and the skill you just learned. Is the following equation balanced? Here's what I like to do. I just start from the left and I start T-charting. I got Fe. On the reactant side, I got 4 Fe's. On the product side, I have 2 times 2 is 4 Fe's. Perfect. And then I have 3 O's, 3 O2's. So that would be 6. And then this 2 multiplies to the O as well. So 3 times 2 is 6. So yes, the equation is balanced. 4 and 6, both on the reactant side and the product side. RYP. So is this one balanced? I can already tell you it's not, because look over on the reactant side, 1 Al, 1 aluminum. But on the product side, 2 Als. So it is not. Oh, and then you can also see the O's messed up. There's 2 O's on this side, and then 3 O's on the reactant side. Nope, the product side. Sorry. RYP for product on the right. Yep. So again, this equation's balanced. Well, look, you can see 4 Als, 4 aluminum atoms on the reactant side. Over on this side, you have Al. You only have 1 Al over here. So just based on this equation, you can see that the aluminum's off, right? It doesn't even matter if the rest of it's right, but clearly it's not. All it takes is 1 measly atom to not be correct to make the whole equation not balanced. Lots of practice here, checking to see if it's balanced or not. Really, what they want to do is they want to know that you know how to count elements and atoms when you're looking at equations. And if you can do that, you're not going to have any problem with any of this. And that's why we've given you that T-chart strategy. If you T-chart your chemical equations, you're not going to have any problems. So you're going to get a lot of practice in T-charting. So again, you're going to T-chart. You're going to T-chart the reactants. You're going to T-chart the products. You can do that for all of these. And if it checks all the way down, if it's balanced on both sides all the way down, then you would mark balance correctly. If it's not, if one is messed up, it's not balanced correctly. Even if you don't do these, just make sure you go and verify that you can see the errors, you can see the mistakes, because when you come face to face with this question on a unit test, on a STAR test, you cannot make any mistakes. No time for mistakes. Friends, and that is the end of the law of conservation of mass. So you're going to get some practice in class, and we'll talk soon. Thanks.